So this is the tail end of a section that I don't know why I didn't finish this last week, but there it is. Stoichiometry of Electrolysis. So we were talking about electrolysis. These are redox reactions that need an external power source for them to occur. So here we have an electrolytic cell where we've got a copper electrode here, and we have a spoon, it looks like, that we're going to plate with copper. So these two half cells are the same thing, and in fact there's not really two cells, it's all one container. But the voltage source here will cause the reaction to occur where we dissolve copper here, forming copper 2 ions, and over here we are plating copper onto the spoon. So we've got oxidation and reduction. This reaction requires 2 moles of electrons for every mole of copper. And so you can do stoichiometry with electrolysis. Yes?
So when the anode is transferring the electrons to the cathode, does that mean that it's also losing mass?
Yes, the anode would be losing mass because as electrons are sent up here, then copper atoms become copper ions and are aqueous and drift away. And those copper ions end up over here where they pick up the electrons again at the spoon, and then they're copper atoms, and then they're on the spoon.
Okay, it's kind of transferring mass.
Yep, they're transferring mass from this electrode to the spoon.
And how do you know if, like, the amount? That's where you start doing the stoichiometry to see, like, the amount of mass that's being transferred?
Right, so you could, by measuring the amount of current, you could figure out the mass of copper that has been transferred from the electrode to the spoon.
So would like a potential question kind of be like,
A potential question?
A potential question be like along the lines of like almost kind of like a theoretical yield of like electrons given a certain mass of some half cell.
Yeah, something like that. You realize that was a pun? A potential question? Yeah. So we don't measure electrons in terms of mass because, they're really small. Which reminds me of a great T-shirt my husband had. It said something like, "Electrons have mass? I didn't even know they were Catholic." Yeah. Right? It's really bad. It's so funny. Okay, so we measure electrons with charge instead of mass. And so we've got our Faraday constant, 96,485 coulombs per mole of electrons. And we remember that 1 amp is, that's a measure of current, is 1 coulomb per second. So we've got coulombs here, we've got coulombs there, and we've got seconds. So the current in coulombs per second times time will give us the charge. And basically problems like this just come down to unit analysis. Put these different things together so the units work out. So here's an example. Silver can be plated out of a solution containing silver ions according to the half reaction. How much time in minutes would it take to plate 12 grams of silver using a current of 3 amps? So this is a potential question, except it has nothing to do with potential, right? So let's write down a couple of things so we don't forget that they exist. Faraday's constant, 96,485 coulombs per second. I will give you that number on an exam. Here we've got 3 amps of current. That's equal to 3 coulombs per second. So we have some information here. Approaching this as a dimensional analysis problem, we need to figure out where we're starting and where we're going to end up. There are 2 numbers given in the problem, 12 grams of silver and 3 amps. we need to remember that amp is actually coulombs per second. And so then you have to decide, am I starting with 12 or am I starting with 3? And my general recommendation is look at the units. So this looks like a single unit, but that's actually a derived unit, coulombs per second. So that could be used as a conversion factor. 12 grams of silver is just 12 grams of silver. It can't be used as a conversion factor. So that's what we're going to start with. Okay? And if this is something you struggle with, then you should definitely write out a path. And you got 12 grams of silver, and you're going to convert and convert and convert and convert, and we're going to end up with minutes. I'm just going to figure it out as we go along because that's what I feel like doing today. So 12 grams of silver. So we're going to have grams of silver down here. What might be a useful thing to convert that to? Moles. So let's convert that to moles of silver. So that would be 107.9. Now we've got moles of silver. The current here is giving us a time unit, so we're going to need that. Do you see what I did up here? That's dumb. It's not per second. Oh. It's per mole electrons. Sorry about that. So here we've got moles of electrons in charge, and here we have charge and time. We want to end up with time, so we need to get to coulombs. We've got moles of electrons here related to coulombs. We've got moles of silver. So we're going to say, well, I want to get rid of moles of silver, so I'm going to put that down here. And I think I could get to moles of electrons here. So I'm going to look at the balanced half reaction here. And that's going to give me the relationship between moles of electrons and moles of silver. And it's 1 to 1. So there's 1 mole of electrons for every 1 mole of silver. Now we want to divide by moles of electrons. And the Faraday constant is going to be useful there. So 96,485 coulombs per mole of electrons. And the moles of electrons cancel out. I'm trying to get to time. This, the current that was given relates coulombs and time. I'm going to divide by coulombs and multiply by time. So this is 3 coulombs per second, which is the same as 1 second per 3 coulombs. You can just put the number on the bottom. You don't have to calculate anything. So now I've gotten to time, but I want minutes. So I'm going to divide by seconds, multiply by minutes. 1 minute is equal to 60 seconds. Anybody have any questions about that process?
When you put the seconds over coulombs, that was just rearranging the generic.
Yeah, when I put the seconds over coulombs, I was taking this relationship and putting it in upside down. And I did that just to make the warnings. It's still valid because what this is saying is that 1 second is equal to 3 coulombs in this situation. The numerator is equal to the denominator.
And we chose 3 because that was given. Yeah.
That was given, yeah. So 3 amps is here. Yep.
Okay.
So 12 divided by 107.9 times 96,485 divided by 3 divided by 60. And we come up with 59.6 minutes. And then let's, practice our sig figs. This is 2 sig figs. That one's 4, exact, 5, 2, exact. So we'll go with 2 and say this is 60 minutes. Any questions?
So then the Faraday constant is, well, actually back up. A coulomb is a measure of charge.
A coulomb is a measure of charge.
Well,
An amp is current, which is the rate of charge moving. So it's charge per unit time.
And then the Faraday constant is just relating the amount of charge per
Mole of electrons. And you could take the Faraday constant and figure out what the charge on a single electron was
similar to,
from that.
converting moles to atoms, but like in terms of
Yeah, this is actually probably closest to a molar mass. So, here's silver, 107.9 grams per mole of silver. We don't measure electrons in masses. We measure them in charges. And so this is the molar mass of an electron, but it's a charge.
it's a molar charge.
It's the molar charge, yeah. The charge on a mole of electrons. Yep. Anybody else have any questions? There's like a huge variety of problems that could be asked here. So, it's stoichiometry, done that before, right? But now we're throwing things like current in there, and we're looking at numbers of electrons instead of just masses of products and reactants.
So how many conversions are we really going to have to know, like just to remember?
How many conversions do you have to know?
For like the testing.
Well, I would expect that you know this one. 1 minute and 60 seconds. And how many minutes in an hour? 60, yeah. So that's something I consider to be common knowledge. An amp being equal to a coulomb second, I'll probably give you that somewhere on the list of useful information. But you need to remember that you could even go looking for a relationship there. I'll give you this one because that number is a little tricky to remember. And the point of this is not, can you remember lots of little tiny details? The purpose is, can you put stuff together and solve problems? Do you understand what's going on? Because in practice, unless you use this stuff all the time, you don't necessarily remember that number. I happen to have memorized the molar mass of silver because I keep using it over and over and over again, but I wouldn't expect you to know that.